SwayamPrabha. Digital India. Educated India.
Hello everyone, we were continuing our discussion on combustion of solid propellants, and in the previous lecture we discussed the effect of various influencing parameters on the burning rate of composite propellants, and we have discussed so far the effect of the pressure, effect of ammonium perchlorate crystal size, the other parameters such as like the gas velocity inside the port, the transience effect like the pressure fluctuations can also influence, the vehicle accelerations can also influence the burn rate. However, we need to remember that in the high pressure the mixing process between the gaseous fuel produced due to pyrolysis of the polymeric binder and the oxidizing species produced due to decomposition of ammonium perchlorate is a vital one, because in the high pressure, although the reaction rate is very fast, the diffusion rate is not improved that way. So, in a sense, in the high pressure range the AP composite propellant is dominant by the diffusion process or mixing process between the fuel vapor and the oxidizing species, whereas in the low pressure ammonium perchlorate premix flame dominates. So, this part I think we have discussed thoroughly earlier, and we have seen the effect of ammonium perchlorate crystal size. As the crystal size becomes smaller, the standoff distance becomes smaller, and the heat feedback coming from the gaseous reactions is also going to increase, which will in turn helps in improving the burn rate or enhancing the burn rate. And we should appreciate that the burning rate or the burn rate or the regression rate of solid propellant is very important parameter for the design of rocket motor. So, the influencing parameters we need to understand that what are the major influencing parameters for burning rate of composite propellants, and of course, this diffusional process is very important. That is why the major parameters influencing the burn rate are the pressure and the ammonium perchlorate crystal size. However, there are other parameters which can also influence the burning rate of composite propellants. Now, in today's lecture we will talk about the effect of catalyst on burning rate of composite propellant. I think we have already started our discussion in the previous lecture that there are certain catalyst or burn rate modifiers which can increase the burn rate of composite propellants. Those are termed as the positive catalyst, and there are certain burn rate modifiers which are going to influence the burning rate in such a way that the burn rate is going to decrease. Those are called negative catalysts. So, in this lecture I think we will talk about both the positive catalyst as well as negative catalyst and their role on the burning rate of composite propellants. Now, let us quickly look at what we are talking about here, that if we look at the burning surface here, this one composed of various size of crystals which are like ammonium perchlorate crystals, and we said that there are three flame, let us say they are appearing at a certain plane from a distance x star from the propellant surface. So, this is our flame. So, the heat feedback is coming from the flame to the propellant surface. So, we can say the heat flux feedback from the gas phase to the condense phase at the burning surface is taking place. So, the catalyst can act in both ways, like either it can act on the decomposition of the ammonium perchlorate. So, it can improve the decomposition reactions in the condense phase, or it can act on the reaction in the gas phase of the gaseous decomposition products. So, whatever the reactions is taking place of the gaseous decomposition product, the catalyst can act on that. So, this way it can either increase the burn rate of the propellant or it can decrease the burn rate of the propellant. So, if they are going to increase the burn rate of the propellant, increase the burn rate so we can say the catalyst that increase the burn rate of the propellant, we call them as positive catalyst. For example, we have already seen that some iron oxides like Fe2O3, some organic iron compounds can act as positive catalyst, whereas there are certain catalysts that decreases or reduce the burn rate of propellant are called negative catalyst. Some examples are like lithium fluoride, calcium carbonate, strontium carbonate, SrCO3. So, they act on the reducing the either the decomposition of the ammonium perchlorate or in the gas phase reactions, which in turn influence the burn rate by reducing the burn rate of the propellant. So, there are certain ingredients which may be used in a small amount, but they are having influencing effect in terms of changing the burn rate. Now, let us look at the positive catalyst and then we look at the negative catalyst. So, I think we have already looked at a plot where it shows the change of burn rate versus pressure for various particle size of iron oxide catalyst. So, you can see the non-catalyzed one is shown by the black squared legend. So, this is the non-catalyzed case, this one, whereas for the catalyst case we can see that the burn rate is going to increase as we adding the catalyst, but there is a change we can see here once we reduce the size of the catalyst, because you see this 0.16 is this one is 0.01 0.16 micrometer catalyst size, this one is 0.3 micron, whereas this one is 0.2 micron. So, various size of catalysts have been tried and we are seeing here that as the catalyst size is reducing, the effect on the burn rate is actually improving, because the total surface area of the catalyst particle at a fixed concentration is going to be an important factor, like the surface area of the catalyst. Because that will in turn is going to influence the reaction, is going to influence the reaction rate. Now, the surface area of the catalyst is going to play an important factor for attaining the high catalyst efficiency, and which in turn is going to influence the reaction rate, and eventually that will increase the burn rate of the propellant. Now, if we use a very finely divided iron oxide particles, for example, like 0.2 micron, 0.2 micron means 200 nanometer, 160 nanometer, 300 nanometer, and it can be observed from this plot that compared to the non-catalyzed case, for the catalyzed case the burn rate is going to increase, and as we have smaller size particles for catalyst, we can see the burn rate is actually even higher for small size catalyst compared to the bigger size catalyst. There are other iron or organic iron compounds which are more effective in terms of increasing the burn rate, because they may form like discrete iron oxide particles during their decompositions. So, certain organic iron compounds, for example, like N-butyl ferrocene, there are other also N-butyl di-N-butyl ferrocene, iron acetate, hydrated ferric oxides. So, there are certain iron compounds which can be more which was found out to be more effective, because upon decomposition of these catalysts is going to produce very fine iron oxide, which in turn is going to help in improving the reaction rate of the propellant, and which in turn is going to increase the burn rate of the propellant. Now, they is going to bonded with the polymers like the HTPB polymer or even polyester polymers, which are used as binder. So, basically the catalysts are bonded to the polymers which are used as binders in the propellant. Now, there are other catalysts which have been tried. For example, like if you look at this plot, we can see there are other catalysts which is showing almost like 10 folds of increase in burn rate. If we see here that almost for all pressure cases, for non-catalyzed versus catalyzed, if you look at this one is like N-hexyl carborane. There are other, of course, carboranes are used, N-butyl carborane, there are isobutyl carborane IBC, and then N-hexyl carborane or NHC. Now, why they are very important in terms of catalysts? Just because the carborane contains carbon, hydrogen and boron atoms. Now, once they decompose, so once the carborane goes into thermal decomposition, it produces boron atoms. Which is highly energetic. If you recall our discussion on the solid propellants, during that time I think we talked about the different type of metallic fuels. If you recall that we talked about the metallic fuels, we talked about the different polymeric binder, we talked about the different oxidizers. In terms of fuel, we have said that there are different metallic fuel which are tried as the fuel part of the propellant. In that sense, we have said that boron is one of the important fuel, because it has high gravimetric and volumetric heating values, and in case of this catalyst, carborane type of catalyst, they are going to, once decomposed, they are going to form like boron atoms, which are highly energetic, and it is going to be oxidized by oxidizing fragments formed from the AP decomposition, and that is going to react with that oxidizing fragments or oxidizing species. So, that will eventually is going to produce high heat at the burning surface, and that in turn is going to enhance the decomposition of the AP particles and of the binder present in the burning surface. So, what we are just saying here, that the catalysts are present, ammonium perchlorates are also present, So, ammonium perchlorate is present and these are bonded in the HTPB binder. So, if you recall the normal reaction mechanism or the burning mechanism of composite propellant, what we said that ammonium perchlorate is going to produce some APPF or ammonium perchlorate premix flame, your fuel is going to produce some fuel vapor which is going to mix and they are going to produce some primary diffusion flame and later on they are going to form some secondary diffusion flame or final diffusion flame. So, once you add this carborane type of catalyst, what is happening upon decomposition of the carborane, they are going to form some boron atoms, they are going to form some boron atoms and these boron atoms is going to oxidize by the presence of the oxidizing species produced due to the decomposition of the ammonium perchlorate. So, once the boron particles react with oxidizing species, they are going to produce high heat. So, which in turn is going to increase the temperature of the gaseous species and is going to improve the heat feedback coming from the gas phase reactions. So, the boron particles burn in this zone and is going to provide the heat feedback to the propellant surface or the burning surface of the propellant, which in turn is going to improve the decomposition of ammonium perchlorate as well as the pyrolysis of the HTPB or the polymeric binder, which in turn is going to increase the regression rate of the propellant or the burn rate of the propellant. So, the positive catalysts play a role either by improving the decomposition of the ammonium perchlorate or the polymeric binder, pyrolysis of polymer binder, or it can eventually going to improve the gas phase reactions happening in the flame zone. So, in a sense the catalyst ultimately is going to increase the burn rate of the propellant and that is why they are called positive catalyst. Now, interestingly we have to look at one more thing here, that if we look at the for any percentage of catalyst such as iron oxide catalyst, the burning rate increases with decreasing D0 of the catalyst here Fe23 catalyst. Now, value wise if you look at the addition of particle, for example, like let us say if we just consider any particular pressure, let us say 2 MPa or maybe some 5 MPa. Here you can see once you add the catalyst, the burning rate is increasing from about it was somewhere over here for non catalyst case, which is going to increase to here for catalyst case. If you decrease the particle size, it may go even higher. Okay. Now, the surface area of each of these Fe2O3 particles plays very crucial role in its catalytic effect. Now, since the pressure component exponent remains almost unchanged upon the addition of the Fe2O3 catalyst, we can say the catalyst is considered to be the more effective in increasing the rate of gas phase reaction rather than having effect on the reaction in the condensed phase. So, in experiment it has been observed that the pressure exponent does not change much for the Fe2O3 catalyzed propellant. Therefore, we can say that it is more effective in increasing the reaction rate of the gas phase reactions rather than playing an effect or playing a positive effect in the condensed phase reactions, because the pressure exponent is not changing that much. But there are certain catalysts which can improve the condensed phase reactions, or sometime like it can improve the decomposition of ammonium perchlorate, for example, like certain oxides which can play a role in improving the decomposition of ammonium perchlorate, or it can change the thermal decomposition of ammonium perchlorate by reducing its temperature, or some high temperature decomposition and low temperature decompositions. Those processes can be modified by presence of some oxide catalyst. There are other catalysts, for example, like copper chromate CuCrO4 copper chromate, but it can improve the burn rate of the composite propellant, but it may compromise with the thermal stability of the propellant. Generally, once we add copper chromate with the ammonium perchlorate based composite propellant, the thermal stability of the propellant is kind of lowered, and sometimes it is lead to some spontaneous ignition. So, that way it is not very thermally stable, and in that sense copper chromate cannot be considered to be a good catalyst, because it is actually leading to some degrading quality of the composite propellant. However, carburants are kind of effective catalyst in improving the burn rate, because you can see it can increase the burn rate in terms of like values almost like 10 times for various pressure ranges. And the major reason for this one is that the thermal decomposition of carbon is going to produce boron atoms, which is highly energetic, and that is going to react with the oxidizing species formed due to the decomposition of ammonium perchlorate, which in turn is going to increase the heat release in the reaction, and that will improve the heat feedback coming from the gaseous reaction zone to the condense zone at the burning surface, and which in turn is going to increase the burn rate. So, these are like positive catalysts which is going to increase the burn rate of the propellant, but there are certain catalysts which can decrease the burn rate of the propellant. For example, like lithium fluoride, we have already said that there are certain catalysts which can negatively impact the burn rate of the propellant. Those are called negative catalyst. So, one such catalyst is lithium fluoride, and you can compare the thermal decomposition data of lithium fluoride compared to like ammonium perchlorate. So, if you look at the top figure here, this was actually we have seen earlier that this is the typical ammonium perchlorate decomposition. So, this is typically like TGA DTA curve we have seen. It is like the mass loss, this one is the mass curve, this one, whereas this one is the DTA one, which tells us like the exothermic and endothermic peaks. So, this part we have already seen, because this is non catalyzed case. So, we can see there are exothermic peak here and endothermic peak here because of the decomposition and melting, and here exothermic reaction is taking place or because of the decomposition. This one is like around 525 or so. Now, once we add like 10% lithium fluoride, the thermal decomposition process is actually modified. Now, instead of having single exothermic peak, it is showing two exothermic peak. One is here, second one is at beyond like 750 Kelvin, whereas the first one is kind of modified to a slightly lower temperature what we have seen there. So, we can see also the endothermic peak is observed at around 516 Kelvin, 516 Kelvin. The exothermic peak originally was at 725, now appears at 635 Kelvin, and the endothermic reaction occurs between like 520 to 532 Kelvin, this this endothermic reactions. Now, we are seeing an additional exothermic peak here, which is temperature region beyond 720 or 750 to 790 Kelvin. So, two exothermic peaks we can see here. Now, we should also look at what is exactly happening here, because if you look at the decomposition reactions, primary endothermic reactions are like NH4ClO4 plus, so it is like one NH4ClO4, which is the balanced one is like something like this. So, sorry, this is LiF, which is going to form like 0.497 NH4 unreacted one plus 0.503 ammonium fluoride plus lithium perchlorate LiClO4. LiClO4 is lithium perchlorate. Now, this is going to decompose further and is going to form the lithium chloride and oxygen. So, this is going to decompose further and is going to produce oxygen plus lithium chloride. So, we can say that the first stage decomposition reaction will be like going to produce ammonia, because ammonium perchlorate is going to produce ammonia plus perchloric acid plus that lithium perchlorate. And in the second stage reaction, second stage decomposition, we can say that this ammonium perchlorate is going to decompose further and is going to form oxygen plus lithium chloride. So, we can say that upon addition of 10% of lithium fluoride, the decomposition process of ammonium perchlorate is going to be modified and the decomposition reaction will be changed to this, because earlier we have seen that ammonium perchlorate decomposition will form like perchloric acid, ammonia, and then will further going to produce oxygen and HCl. However, once you add 10% of lithium fluoride, this will going to change the decomposition reaction and it will produce this type of species. Of course, oxidizing species are present there, but it is going to change. So, what we can say that the decomposition process of ammonium perchlorate is going to be altered by the addition of 10% lithium fluoride. Of course, this is for a particular fixed amount, but there may be a different amount can be tried. So, due to the rapid decomposition and gasification beyond certain temperature like 630 Kelvin or even higher, the liquefied residue is going to remains. Now, that residue can be stay up to certain temperature like 720 or 750, and that is going to decompose further and is going to finally is going to produce the residue as lithium chloride, because that is after the second stage decomposition. So, lithium chloride is going to produce. Now, if you look at the burning characteristics of the lithium fluoride loaded ammonium perchlorate based composite propellant, what you can see is the burning rate of the lithium fluoride loaded solid propellant. We can see this is like without lithium fluoride catalyst. Now, once we add some percentage of lithium fluoride like 0.5, 1%, 2%, we can see the burning rate is going to decrease. As you can see, this is decreasing in nature, because you compare just take any of the pressure data, we can see here the burn rate is going to decrease, it is decreasing for any case. Like if you consider 2 MPa pressure also, you see the burning rate is going to decrease. Interestingly, it is not only decrease, but there are certain point where flame is going to extinguish also, is going to extinguish. You see there are certain cases where not only decreases the burn rate, but also inhibits the steady state combustion below a certain pressure. So, that will lead to some self extinction, it is mentioned here. So, lithium fluoride is not going to only decrease the burn rate of the propellant, but also at certain pressure it may lead to extinction of the flame. So, this is going to cause the putting of the flame. Now, if you look at this left hand side figure, here it is like discussed about lithium fluoride with 0.5% concentration and compared with the non catalyzed case. The burn rate reduction of the lithium fluoride is due to modification of the condensed phase reactions, we have already said earlier, because that is modifying the condensed phase reactions of AP. But when the particles are decomposed, finally the burning surface will lead to certain condensed phase product like lithium chloride particles that will remain on the quenched burning surface. What we have just said in the reaction, that this lithium chloride will be remain in the burning surface, and that has been shown through some these reactions through the micrographs of the quenched ammonium composite propellant burning surface without lithium fluoride case and with lithium fluoride case. So, for A, this is without lithium fluoride, that is non catalyzed case, whereas the 0.5% lithium fluoride case, this is showing the quenched product which is going to stay there as the lithium chloride, whereas in case of ammonium perchlorate composite case, no ammonium perchlorate particles were present in the case of non catalyzed case. So, eventually we can say that this is going to decrease or reduce the burn rate of the composite propellant if we add lithium fluoride. So, there are certain oxidizers which can improve the burn rate or increase the burn rate of the propellant, whereas there are certain catalysts which can actually play a role in decreasing the burn rate by modifying the condensed phase reactions or by modifying the gas phase reactions. As we have seen that ammonia in case of ammonium perchlorate based solid propellants, once we add iron oxide Fe2O3 as catalyst, they can increase the burn rate by modifying the gas phase reactions, whereas they do not participate in the modifying the condensed phase or decomposition of ammonium perchlorate, whereas in case of negative catalyst, for example, like lithium fluoride, it can change the decomposition processes of ammonium perchlorate and thereby reducing the burn rate. Now, with that I think we close our discussion on the burn rate mechanism of ammonium perchlorate based composite propellants, but there are other categories of propellants. If we recall that we discussed about classification of classification of solid propellants in terms of like homogeneous propellant or double base propellant, then we said composite propellant or heterogeneous propellant. We also said like nitramine propellants, and we have said that composite modified double base. So, I think we should spend some time on discussing about the burning mechanism of nitramine propellants, or first we talk about the thermal decomposition of the nitramine like HMX or an RDX, and then we will briefly talk about the burning mechanisms of the nitramine propellants, and then I think we should spend some time on discussing the AP CMDB or AP loaded composite modified double base propellant and the nitramine loaded composite modified double base propellant, because we have seen earlier in the discussion that the double base propellant can be modified by adding some ammonium perchlorate as additional oxidizer or HMX or RDX as additional oxidizer, and then the propellant will be changed to composite modified double base. So, I think we should also discuss about the burning mechanism of those, and then I think we can close the module on the burning mechanisms. All right. So, we will talk in the next lecture. Thank you.